Hello there guys, Teacher Krishna here and welcome to our next class for the 4th unit. Just like you know, this is a class that is part of the high school and 10th high school. Our subject is physics and we are working on week number 29 today. So let's go over our presentation and let's start with our end in mind. Students will be able to explain the relationship and behavior of the mass and weight of objects in different scenarios. And for today, you have a list of activities right here. Number 1, read and summarize topic 3.06 and complete the exercises from page number 2. So, just like every week, I'm going to give you the theory, I'm going to give you some examples of several problems that you can complete, and then you need to go to page number 2 and complete some exercises by yourselves. So, of course, you can put into practice all the knowledge that you are acquiring from here. Then number 2, study the topic and participate in the live discussion in Zoom. Then number 3, take the assessment for topic 3.06. If you have any questions, you can let me know during the Zoom session or you can directly ask me in WhatsApp. So let's start, and today we're going to talk about a very simple topic, which is mass and weight. Even though it is very simple to study, we still need to consider some important differences so we don't mix up things. So, I really like this image because it clearly represents a very huge difference that we have between mass and weight. Because people tend to misunderstand both terms, and they tend to think that actually both terms are referring to the same thing, when in reality they are not. So when we talk about mass, or let's go over the theory that we have right here so we can observe the differences, and then I will go back to the image. So this is a general view taken from Paul Hewig's work, in which mass is the amount of material immersed in an object. This quantity only depends on the types and amount of atoms in the substance or object. So, for example, if we are talking about atoms of gold, let's say, so mass is only going to depend on the properties of gold itself. We can also talk about other things or other elements such as oxygen. So a mass of oxygen will only depend on the atoms of that specific element. So how is weight different? So weight, it depends on the object's location. And please make sure to remember that clearly, an object's location. And it is necessary to take into consideration the mass of the object as well as the gravitational pull of the location. For example, a rock found on Earth will only have 1/6 of its original weight if it is positioned on the moon. So, basically this one is the clear difference that we can see. Mass, it only depends on the properties of the atoms that are in a certain substance. And when we talk about weight, we need to take into consideration the gravitational pull of the object that is attracting the object that we are analyzing. Which in this case, if we are talking about a person's weight, then a person's weight on Earth will need to take into consideration the person's mass and of course the gravitational pull of the celestial body as well. But anyways, let's continue, and now we need to take into consideration some units for measuring mass and weight. And remember, mass does not equal weight. They are different things. So for mass, it is usually measured in kilograms. And remember that we have studied the conversions from one unit to another, and kilograms is usually used in the international system. So there are other units of measurement that you can use as well, and they can be grams, milligrams, and slug. But the most used is kilograms. All right, and then we also talk about the units for weight. It is measured in newtons. One more time, newtons is the unit that is regularly used in the international system. Although we can also use other ones, which can be done in pound. And even though mass and weight are not the same, they are proportional to each other. So remember that when we say that something is proportional to another thing, it means that if one value increases, the other one will actually do the same. or if one value decreases, the other one is going to decrease as well. And how can we represent this in a very general example? So basically, if a mass has a very big, if an object has a very big mass, then it is going to have a very big weight as well. And if an object is very light, let's say, then it is going to have a lower weight as well. All right, for you to take it into consideration. So now we're going to analyze a little bit more about the relationship between mass and weight. And here you have the equation relating mass and weight on Earth. And it is equal to weight equals mass times gravity. So basically W is the weight of the object in newtons, M is the mass of the object in kilograms, and letter G is going to represent the acceleration due to gravity, which on Earth is 9.81 meters per second squared. And this is a value that is going to be used in many different physics problems. So make sure the value of gravity, 9.81 meters per second squared. All right, let's continue. And let's continue, of course, with the relationship between mass and weight. Remember that the weight of an object on Earth may be found by using this equation. So here we have another a formula that we have studied before, and it is, of course, related to one of the Newton's laws. And in this case, the law of universal gravitation, from what I remember, about Newton. Okay, and we can also take into consideration the formula that we have studied before, in which G is the constant for gravity. We have the mass of an object, as well as the mass of another object divided by the distance squared. So in this case, Fg will be the gravitational force, and Wo will be the weight of the object. And remember that our constant in G, or our constant for gravitation, equals 6.67 in elevated to the minus 11th power newtons per meter squared per kilograms squared. Well, I'm sorry, it should be newtons times meter squared per kilogram squared. There you go. And so something important to notice as well is that E is going to be substituted by times 10. So in this case, when you operate it in your calculator, it will have to be 6.67 times 10 elevated to the minus 11th power. Then MO is going to be mass of the object. ME is going to be the mass of Earth. The square is going to be the distance between the object and the Earth squared. And we can combine these equations since they are both equal to weight. So sometimes this happens in physics. So if you have actually two formulas that are going to equal the same value or the same term that we are looking for, we can actually combine them in order to find another unit or another value that we don't have in the problem that we are analyzing. So in this case, just like you can notice, we can have mass times gravity. And mass times gravity is the weight, basically. And the gravitational force is the formula that you have on our right, which will be G, MO, ME, divided by D squared. So what happens is that you can notice that in both sides, we have the mass of the object. So if we actually try to substitute it, we can just eliminate it. Because if we transfer the mass of the object from our left to the right, then since it is multiplying, it will start dividing. So we can just eliminate both of them. So since it cancels out, then we are going to have this remaining formula, in which gravity equals the constant of gravity times the mass of Earth divided by the distance squared. And how do we explain, or how do we word this formula out? And it says the acceleration in a vacuum does not depend on the mass. Isn't this what Galileo stated? So there is a very interesting experiment that you can actually look for online if you're willing to. But basically, a vacuum is a certain location where there is no air at all. So if you have a bowling ball on one side and you have a feather on the other side, and you actually let them go at the same time, they are going to touch the ground at the same time. And why does that happen? Because, just like it is stated right here, and just like Galileo once mentioned, in the vacuum, the acceleration is not dependent on the mass of the objects that you are analyzing. Okay, and let's go a little bit faster because we're running out of time. So, application exercises. Here is practice number 1. True or false? A 2 kilogram iron block has twice as much inertia as a 1 kilogram block of iron. Number 2, a 2 kilogram iron block has twice as much mass as a 1 kilogram block of iron. And number 3, a 2 kilogram iron block has twice as much volume as a 1 kilogram block of iron. And number 4, a 2 kilogram iron block has twice as much weight as a 1 kilogram block of iron. So the answer for all of these statements will be actually true. Of course, this is related to each one of the Newton's laws that we have studied before. And of course, they are related to each one of the terms, such as mass, volume, weight, in which it seems we're talking about iron blocks, and we are just actually decreasing the amount by a half. They are going to have the same properties. Now let's go with practice number 2. A 1 kilogram bag of nails weighs 9.81 newtons at the Earth's surface. What is the weight in newtons of 1 kilogram of butter at the Earth's surface? Well, actually, that's going to be pretty much the same. Because remember that we are still analyzing 1 kilogram of butter in, let's say, on Earth's surface. So when we actually use our formula in which weight equals mass times gravity, it will be our mass, which is 1 kilograms, times gravity, which is going to be 9.81. So we're going to get, as a result, 9.81 newtons. It's pretty simple. And lastly, we're going to have practice number 3. The mass of the space shuttle is about 5.0685 kilograms. What will be the weight of the space shuttle as it sits on the launch pad? Be sure to show your work. Alright, now this one is a problem that is a little bit more complex, but let's start with our givens. So we have the mass of our shuttle. So our mass is 5.0685 kilograms. What is the value of gravity on Earth? Is a constant, which is 9.81 meters per second square. Here we have a formula to find the weight of the shuttle when it is actually landing on Earth. So we are going to substitute our mass for 5.0685 kilograms, and of course the value of gravity for 9.81 meters per second square. After we multiply it, as a result, we are going to get 4,963,860 newtons. So if you want to simplify all of this, and of course you want to use math connotation, you can go back right here. So basically, summarized, our weight will be 5.06 newtons. All right, let me check if we have something right here at last. We have practice number 4. I don't think we are going to have enough time to actually finish with this problem right now. So this one is a little bit more complex, but basically, you can pause the video and read. I'm just going to explain the last steps. We're going to have mass number 1. We're going to have mass number 2. We're going to have our distance as well. We have the constant for gravity. And what we are looking for is, of course, for the force. So in this case, we have to use the formula for the universal gravitational law of Newton, in which we can only substitute our value for the constant of g. We have mass 1, mass number 2, divided by the distance squared. And this one will be our result at the end. We're going to expand a little bit more during the session, right? So thank you a lot, guys, for coming, and I will see you in a couple of minutes. Always take care. Goodbye.